Thank you so much for coming. We're going to talk about organizing neuroimaging data at the session and a particular way of organizing data. But before I actually tell you more about this particular standard, let me introduce you to Professor Smith. So Professor Smith is an up-and-coming early career researcher, having plenty of different ideas. She's running her own lab, like some of you already do, or many of you will in the future. And she's always on the lookout for new ideas, new experiments, new projects. And she just realized that she could address one of the questions concerning attention using a data set that was acquired by one of her PhD students before. So basically, its idea is very simple. Can we use eye tracking signals that was acquired because why not for a different experiment during resting state to see whether this participant was actually sleeping or not, and see what are the correlates of this dozing off in the scanner. So then she's like, okay, this is perfect. I've got this new postdoc coming in, and that postdoc can take over that data. Simple, right? Yes, of course. And Mike, who's the PhD student who acquired the data, is a data scientist somewhere in California right now. As you can see, he's wearing the data scientist uniform, shorts, and using data scientist equipment, the surfing board. Well, Mike is unreachable. It was very hard to actually find the data physically, but when that magical USB stick was finally discovered, it turned out that it contains heaps of data in a very disorganized way with different Excel spreadsheets. No one knows what the columns mean. No one knows what the files are. So basically, it's a situation of getting lost in the data that were acquired very close to you. And sometimes, to some extremes, you might even get lost looking at your own data from 5, 6, 10 years ago. And this is problematic from many different points. First of all, it's harder to share data. And when I mean share, I mean it in a broad range. Sharing is also sharing with yourself in the future, but also sharing with your colleagues, sharing with someone from your lab, sharing with a collaborator from a different university. Doesn't necessarily mean publicly sharing, because actually scientists have been sharing data within this very broad definition for many, many years. And then it also requires unnecessary manual metadata input. What does that mean, really, metadata and input? Well, basically, doing analysis, we have to quite often tell the analysis software different parameters that are actually describing the data that we're trying to analyze. And when the data and the parameters or metadata are dissociated, then it's easier to make mistakes. And finally, when we want to validate automatically such data sets, for example, from a point of view of publicly sharing or receiving a data set from a collaborator, that is much harder. You got basically a data set from someone, and it's going to take you a while to figure out if everything is in order. So you have all these problems, but the question is whether there's really nothing we could do about this. Well, fMRI has been done for over 20 years. It's hitting almost 29 now. And during that time, we had like an explosion of papers. There are so many studies in so many different cognitive states and paradigms being researched. MR itself is even older, and it's being used even more, like orders of magnitude more, especially in the clinic when we talk about structural imaging. So there's a lot of data coming in, but what is very interesting about MR specifically, and what actually made us hopeful that we can come up with some standardization, is that there are 4 major MR scanner manufacturers. So most of this data is coming from a limited number of sources. And when you think about the restriction of doing an experiment inside an MR scanner, well, there's also certain limit to what people can do in the scanner, so paradigms cannot be completely crazy. So that gives us initial hope, and I'm just going to make a disclaimer that the standard that we are working on have actually went further than MR, and now we are supporting other types of neuroimaging data, but that was the initial impulse. So the standard itself is called Brain Imaging Data Structure. And it's a data organization and description at the same time. So what I mean by that is that it tells you how your files should be organized, where they should be, how they should be named, but also what file formats you need to do and what metadata you need to provide for each particular type. It's a standard. That means that it's strict. You have to do things in a very specific way, which enables computer machines API programs to actually read the metadata. And just to reiterate who's it for, especially lab PIs and anyone who is managing larger groups or even smaller groups of researchers. Even if you are working on your data set and you have research assistants or undergraduate helpers, there is collaboration already going on. There is already data sharing going on, and that's why it makes sense to basically agree upon a certain way of how you're going to organize your data. And then workflow developers, I know at least some of you are designing different workflows, pipelines, methods, and being able to rely on a particular way how data is organized, how the input data is organized, makes your life much easier, especially if we provide tools to validate whether those inputs are organized appropriately. And then finally, database curators. This is a much smaller group, but it's important, especially now when we're seeing more and more data sharing, more requirements for data sharing on repositories. Actually, taking in those data sets is tricky, and it's time-consuming to validate those, but that's helping. So in other words, what we aim to provide is a language. It's basically a way for different participants of this community to talk about their data. So we have data producers that provide the data, and then we have different applications such as quality control tools, as well as data processing pipelines. But then we have also repositories, and we have collaborators, and now we all can speak the same language. So when we started this project, we really wanted it's to be successful and highly adopted, widely adopted. And that's why we went the long route of making the community project. So we really wanted to hear everyone's use case. We really wanted to have as many scientists involved in this project as possible, and we still do. And the project is still living on. I'm going to talk about this, the existing extension and ongoing work a little bit at the end. We also did not want to reinvent the wheel. We didn't want to create something completely brand new unless it's absolutely necessary. So we did talk to people and ask them, like, what do you do in your labs? Because many labs already have certain internal standards for describing and organizing the data. And we wanted to build on top of that. We wanted to reuse existing file formats instead of creating a new one unless it's absolutely necessary. And finally, the 80-20 rule. So we didn't want to be bogged down trying to figure out edge cases that happen very, very rarely. We wanted to cover the 80% of the cases in 20% of the time. And that was very important, and we have to constantly remind ourselves that the goal is to fix the most common cases, even though it's easy to spend a lot of time discussing some edge case. So, what is BIDS really in practice? Basically, we're trying to go from this unstructured heap of raw data put out by your scanner and other instruments, because we're talking also about behavioral data, we're talking about physiological data, and things like that, into a neat, organized file folder structure with names that are intuitive yet formalized, as well as file formats that contain data in a machine readable way. And speaking of those file formats, we are using, we're using tab-separated value files for tabular data, very simple text file format that is readable by many, many different tools, including pandas, as well as MATLAB and R tools, etc., etc. And that file format is used throughout the structure. Here I'm showing you the participants.tsv file, the very top level of the organization. And that top level describes basically demographics. So this is where you're going to put things like age, gender, and stuff like that. We have provisions for putting large amount of questionnaire data. So if you administered like 40 different questionnaires, you want to have item data. It's also possible, and you can split those into individual files. So we also accommodate that use case. And you probably noticed that there's a structure of folders denoting different participants. There's a sub-01, sub-02, sub-03. Those are basically data from a particular participant. And underneath that, you have different modalities, and inside those, you have different data types. And speaking of data, for the binary MR imaging data, we're using Nifty and a couple more file formats for a recently merged MEG extension that I can go over in detail if there's need for that. We're allowing both uncompressed and compressed Nifty, and just to kind of answer questions why Nifty and not other file format. It's basically the most commonly used file format out there, and it seems to be meeting the requirements of most use cases out there, with some exceptions, obviously. And we're using this for both structural data, so T1 weighted images, as well as diffusion, so DWI, and as well as fMRI. And you probably noticed that each of these files have the structure of a key hyphen value underscore key hyphen value underscore form. And that's standard across all of the file names. For example, you have subject participant 01, task rest underscore bold. We had a lot of discussions how to denote resting state, and basically the conclusion was that resting state is nothing else than a very unspecific task. And this is how this was resolved. And then we also have JSON files, and those are dictionaries of metadata. This is where you're going to have a controlled vocabulary of keys, and each of them has a definition in the specification, so you know what they mean. Many of them are related directly to DICOM fields. And we really focused on the fields that are necessary or very useful in data analysis, such as repetition time, slice timing, and things like that. So this is where those pieces of metadata can go. And then finally, this whole specification that took quite a while to put together would be, there's a very long document that might be a little bit tricky to follow, but we also put a lot of effort into building a tool to validate your data sets. So when you're trying to, or you're in the process, or in the process of converting your data to bits, you can have almost real-time feedback on whether you have any issues still to resolve, or whether your job is done. And this is the validator, which is a very nifty JavaScript tool, which means that you can run on the command line like any other command line tool, as well as in the browser. So you can just go to this website. I'm going to go do all of that together in a moment. point to the folder where your bits dataset is, and it will tell you whether there are any errors or other issues with that particular dataset. And that is happening completely client-side, so this is basically a static page, so none of your data is actually shared or uploaded anywhere, which is useful for sensitive data. Okay, with these resources and this form of a standard, we can revisit Professor Smith, who, with her next project and next data acquisition, can now either do this herself or tell some of her students to adhere to a standard operating procedure such as bits, and then in the future basically living in this standardized, well-defined world without any problems with data organization. So I'm going to walk you through a little bit, walk you through some resources that have been put together over the time to help you adopt bits and start using it. So this is part of our website, bits.neuroimaging.io, which lists the resources that are necessary. The most important one is probably the Bit Starter Kit. This is a project that is collaborative, like almost everything we do, supervised by Kirsty and Dora, as well as Elizabeth, and we have a Google Summer of Code student working on it right now, Patrick Park, and I'm going to show you that website in a moment. You can also download examples, both from OpenNeuro, which I'm going to talk about during the next lecture a little bit more, as well as there's a GitHub repository with stripped down versions of those datasets just to explore the structure. And we also have a forum for questions. And I talked that this is a community-driven project, but I think this is the most important aspect of this endeavor. And I cannot really stress this enough, how important it was to go down that route, that we didn't just like sit down with like 4 other people from the same lab and just come up and tell everyone else what to do. We really wanted to hear everyone. We had public call for comments, meetings during conferences, and things like that. And that led to, for example, the paper describing bits having a ton of co-authors from many different labs, which I'm pretty proud of. And that was then carried on with the BitZap paper. I'm going to talk about BitZaps during the next lecture. We had some meetings dedicated to building tools for bids, during which we had a lot of fun, as you can see. And that community is completely open, so I really encourage all of you to join it, and you can contribute in many different ways. We'll be bitsifying our own data in a moment, and probably you might run into some issues with the documentation, and helping making that documentation better for others is already a very valuable contribution. If there is a particular data type or a sequence that is not covered by the standard, you can help us standardize it as well. All of our communications are open. There's a public mailing list. The current draft of the bit specification is also publicly available and open for comments, even anonymous, on Google Drive. And we have sort of organically came to this procedure for extending bits with additional modalities, because this process is harder because of the inclusion of the community. It's more meaningful, and I think it's more sustainable, but it's much harder to reach an agreement with a diverse group of people over 9 different time zones. So the procedure we came up with, if you want to extend the standard with a large chunk of works, I'm not talking about like fixing a typo or adding one type of a file, but something larger. It basically boils down to drafting the extension proposal with a smaller group of experts who have something that you can show everyone else and discuss with the larger community. And while you do that, it's also very useful to provide examples as well as start extending the validator. And I found myself that sometimes things were completely clear in my head, but as soon as I started actually writing some code that was supposed to take advantage of it, things were like, oh yes, we have to actually specify this and that. And then we reached to the broader bits community as well, ask for public comments, and we are trying to reach consensus in terms of merging that particular standards. We update the validator, merge the document, and release a new version. But that's the sort of often highly technical work concerning different details of data, but no less important is work on getting new users and helping new users use bits. And this is, as I mentioned, covered to a large extent by the Bit Starter Kit, which provides its own templates as well as links to external tutorials. And that's a great place to go when you want to get involved and start using it. And we're gonna check it out in a moment. So just to show you a little bit how over the years this project has grown. We at some point a few months ago, a year ago, we did this like very informal call out of like who's using it. We basically got a response from over 60 different labs that are using it, and there are multiple repositories right now that use it. OpenNeuro is using it as well. And if you look at publicly available data that is in BIDS, you can combine data from 20,000 participants at this time. And that includes only unrestricted publicly available data. I'm not talking about anything behind a user agreement, which also means that if all that you're interested in is reusing public data sets, being able to understand the standard and building tools that take advantage of it is very useful. Okay, so this is the only URL that you actually really need to know at the end of this theoretical introduction. But what we're going to do next is we're going to bitsify a data set. So I've got some example data on our hard drive, and I'm going to show you how gradually I can convert it into bits, and then I'm going to do it manually. And it's a bit of a disclaimer in the beginning. I don't expect anyone to actually convert their data manually in that way. But it's a great educational process to learn how different things are named, what's inside those files. But there exist tools that actually can convert data almost fully automatically for you, and I'm going to link to those as well. But it'd be a bit boring to show you how all of this can be done automatically. But now you can learn more about that structure. Okay, so who brought their own data? Excellent. So, for those who did not, so I'm going to bits.neuroimaging.io, and if I go to getting started, I can go to the Bit Starter Kit. And Bit Starter Kit technically it's a GitHub repository with lots of different resources, and also lists different tutorials. And for those that would like to did not bring their own data, would like to work with someone else's data, I recommend checking out this tutorial. which was written by Franklin Feingold from our lab. And this tutorial is using NKI Rockland test retest data, which you can download now and follow this tutorial. It's actually a part of 3 series tutorials where the initial one is something that we're going to do right now, which is converting the data to bits manually to learn more about the format, followed by automating it, or basically writing a custom script that automates your particular conversion of your particular data to bits. And finally, he's also showing how to use a ready tool called HUDIConf to do the conversion. So if you have problems accessing the NKI data, there's another data set. There's another data set as part of the third tutorial, which doesn't load for me for some reason. Which is actually my Connectome, which is the data set that Russ Poldrack acquired by scanning himself 197 times. Okay, cool. I'm going to use the NKI Rockland data and yes. Hey, great. So let me just show you how my data looks like. So I've got this folder here, and this is going to be the root of my data set. And right now, if you have your DICOM files or any other parrec or any raw data, you should create a folder called source data, one word, and put all of that data inside that folder. And this is where we're just going to put the data before the conversion. And it can be in any form and structure as you want. In here, I have a bunch of subfolders. Inside of those subfolders, for example, here I have this folder called ANAT, with a bunch of DICOM files. Probably each of these files corresponds to a different slice. So what I have to do, as you remember, all of the imaging files in BIDS are in NIfTI. So I need to convert from DICOM to NIfTI. And there are multiple DICOM to NIfTI converters, as you know. Some of them support bits directly. And when I mean they support bits, I mean they can extract metadata from DICOMs and put them in that JSON file that bits specifies. So I'm going to start with this anatomical scan, and I'm going to use a tool called DCM to NIIX, developed by Chris Warden, among others. So DCM to NIIX. So I'm going to get this tool, and if I go to releases, I can download this command line tool for 3 major platforms. So I think this is a good time to stop a little bit because getting that tool will be quite important for converting your data. So let's take like a minute or two just to download this and make sure it works. And if anyone has any questions so far, I'm very happy to answer. Yes?
Have you reached out to the clinical imaging community to see about their interest in potentially adding data to this? Rather than these sort of curated things that the labs do, we acquire thousands of images an hour in this country. That could be considered reaching out to like RadNet and other people who do this to see if they might want to get involved.
So yes, so this has mostly penetrated the research community rather than the clinical community, and we talked to many people. We talked to DICOM people as well. I don't think I know anyone from RadNet personally. So in a way, we didn't make a very specific effort to talk to RadNet people, but we did basically try to talk, and we want to talk still to as many. So basically, that's the bottom line. Hook us up. But and also just to clarify, this is not something you can. Well, anyway, it's going to be clear. Like it's a data structure rather than a database. Yes. So yes. That's fine. That means that you will have to figure out a few pieces of metadata, but they're probably going to be very straightforward, those that are required, and we can help you figure those out. If you have, for example, PDFs of the scanning protocol, that might be useful to figure out some of this metadata. Okay, who's got DCM to NIX installed? Excellent. I see there's an overlap between people who have data and who installed DCM to NIX. This is great. Cool. Great. So this is this tool. It's quite old, I have to say. The tool has been developed for many years. So it has a very unusual, or very relatively unusual command line interface. What we basically need to do is, as the instruction says, we call the DCM to NIX. It will not have the .exe or .exe if you're using like a Mac or Linux. And then we have to specify where we want to put the data, and then specify the directory with the DICOMs that we want to convert. But there are other options here. Okay, sorry. There are other options here, as you can see. One of them is this -b. So -b creates that JSON file when you do the conversion, and it's turned on by default. And there's also -ba, which anonymizes the metadata. So it removes information about time and date of the acquisition, which is perceived, at least by some experts, as non-HIPAA compliant. And that's also turned on by default. What we want to turn on, though, is compression, because we want to make .nii, .gz files instead of uncompressed files. And to do that, we need to switch to the -z flag. So I'm here. I want to convert files from the ANAT folder. So I'm going to DCM to NIX. Output folder will be the root of my bits directory for now. So there will be data, NKI, and then I'm going to do Z as compression equals Y, and this. Oh wait, sorry. Whoop. It's like extreme programming, isn't it? Like with the whole room telling you all the things that you did wrong. Okay, so I've converted one scan to Nifty. If I go to my folder here, 2 files appeared. We need to all get to that stage, basically. So I'll let you convert your file. I recommend starting with an atomical, but you can UBU and start with functional or diffusion or anything else. So what you see here is a JSON file. So someone at some point thought it would be a great idea to write a text editor in JavaScript because it's going to be so quick and fast to load with no waiting whatsoever. Okay. And inside this JSON file, you see that the converter extracted a bunch of metadata from that Nifty file and put it in here. And this is very convenient. And for many types of scans, this can be done completely automatically, but not for all. DICOM coming from certain manufacturers does not include the robots are coming. Does not include certain pieces of metadata that you might have to include manually. And that is, for example, problematic with Philips scanners or some GE scanners. Okay, so we have this JSON file, and we have this other Nifty file. But this doesn't look neat. This is not the structure of the subject ANAT folders I was showing you in the figure. So what we need to do is, first of all, I'm gonna cut or copy those files, and I'm gonna create a new folder. I'm gonna call it subject 01. It's the first subject. And a note here, the 01 is a label, and you can use any alphanumerical label to identify your subject as long as each of them has a unique identifier. So this could be anything. This could be, control 01 or skiz 05 or whatever you think is appropriate. But it has to have the sub dash prefix. Okay, as you remember, here we need to have another folder called ANAT for anatomical scans. And now we copy it here. Okay, this is great. I need to also add one more file in the very top. And this is quite important. Right. I need a dataset description.json file, and each dataset needs to have this this one file, and you can put metadata about the dataset, such as who created it, what's the license of it, what's the description of it, which bits version was used to curate it, and things like that. But there are two fields that are compulsory. So a JSON file, just to add a little bit more background, a JSON file is a dictionary file which uses curly brackets to open and close, and then uses double quotes to escape key values. So you got two fields, bits version, and I'm going to use 1.1.1, and name. And those fields are defined in the standard. I'm going to show you right now. Example. Okay. Cool. So if I go to the bits.neuroimaging.io page, I can download the specification, which is a PDF document. And here, among many different other files, we can go to dataset description. And this is basically a document that you will revisit, trying to figure out how to organize your data. So this is the dataset_description.json file, which has the following fields. And as you can see, some of them are required, some of them are recommended, and some of them are optional. So you have to at least put the required ones, and one of them is bits version, which is the version of the standard that we're using, and we're using the 1.1.1 version, and the name, which is also required. So that's how I know what to put in this particular. Okay. So now, I promised that we're going to have a helper. So I'm going to use the bits validator. You can basically Google bits validator, and you can find it. There's also a link to it from bits.neuroimaging.io. And this is, again, a GitHub repository, just emphasizing this is all a community project. So if you found a bug in the validator, or you want to add additional check in the validator, all contributions are very much welcome, including documentation as well. But the first thing you can learn about the validator is how to use it. And there are two modes. As I mentioned, a command line tool, as well as a web-based solution. We're going to use the web-based one because it doesn't require us to install anything, and you can just use it from any Chrome or Firefox browser. So, sorry, Edge. Anyone using Edge? Well, there's Opera as well, yes? And Safari? No, Opera, Edge. You're using Edge? Using Opera, okay. So yes, so we're going to go to this page. And that is the validator. So here I can navigate to the folder where my files are. And what is important is that I will point to the root directory, which is the directory that contains the source data folder and the sub-01 folder. I click upload, which is misleading because actually nothing gets uploaded. You can do it in you can do it in airplane mode. It's just, this is how the API of Chrome is designed, that this button always has to say upload, but nothing is uploaded. You can check it. And now the analysis was completed, and we've learned a few things. There are two errors. 0 subjects, which is already concerning because there should be at least one. And one session, the whole thing is very big. So what is going on here? And we have an error telling us that these two files are not named in the way that bits instruct us to do. We also got another error saying that there's this subject 01, but actually there's no bits compatible data in it. Okay, so what did we do wrong? Let's go back to the specification and see how these things have to look like. Well, the files need to be named according to this scheme: sub dash, name of the subject, underscore T1 weighted image, if this is T1 weighted image. Let me just check very quickly. But it's saved and sorry, whether I'm not like converting a T2 image. Looks very T1-ish to me. Perfect. So you have to rename it now. So, sub dash, what should I write?
01.
01, okay. What's next? Like that? Underscore. Yes, underscore. Yes. Okay. Here? No. Is anyone listening? Okay. Great. And because this JSON file describes that nifty file, it has to have the same name with exception of the extension. That's why we call this a sidecar file. Subject 01 T1 weighted.json. Okay. Let's go back to the validator, choose a file. Success! This is a valid bits data set with one subject and one scan, and we did it. Yes. So how are your conversions going? Did anyone manage to get to like a clean one subject, one data type? Yes. You did. Okay, excellent. Have one success story, which is all I need, really. Anyone run into any troubles I can help with? Okay, let's carry on and let's add some functional data. Sorry, let me just see what do we have here. We have this breath hold paradigm. So let's convert that. Yeah, right. So it's a great question. Let me just repeat this. What do we do with longitudinal studies where there are multiple visits? People come over multiple days. Maybe there is like a first session and they like run on a treadmill, or they like learn how to be a taxi driver for 3 months and they come back. Yes? All right. So let me just show you how does this look, and that'll be quicker. So for that particular case, because what we figured out is that the majority of data sets are cross-sectional, not longitudinal. So we decided, for better or worse, that the additional hierarchy level for denoting multiple sessions should be optional. So that's why you haven't seen sessions yet, but it basically looks like this. So you have the subject, and inside the subject, you don't go immediately into ANAT or FUNC or DWI. You have another folder for denoting sessions. And please also note that that session is also in all of the file names. And the fact that there is some redundancy, so you have this information and this information both in the file name as well as the location of the file name, because it is in that folder, is actually an intentional feature, because that allows you to, for example, quickly copy all of those files to a temporary folder and they will not override each other, which could be useful for some applications. So this is how you would do a multi-session data set. And we also have a rather liberal definition of what a session is. So a lot of the discussions concerning the standard is what things are. And in terms of session, it's basically a logical grouping of scans, which means that it doesn't necessarily mean an uninterrupted stay of the participant inside the scanner. So if you have a scanning session, you scan the participant, and in the middle of it, the participant says they need to go pee-pee, you can still use that as a logical session, the scans before and after pee-pee. Oh. Yes, so the session folder, you can skip that level if you don't have multiple sessions. So if you're in that like 70 or 80% of people who have cross-sectional studies and they don't invite participants again, you have one level less of stuff. And as I said, for better or worse, I'm flipping every other day whether that was a good decision or not, but it is what it is. Like, this is the standard right now. Okay, so let's see how the conversion went. Okay, so we have a new file to play with. Again, we have a JSON file. Yeah, before it shows up, what are the important pieces of metadata for an fMRI acquisition? What are the things that we cannot do anything without? Nah, anyone? TR? Yes. Anything else that is super useful or could be useful depending which school of analysis you come from. Like, yes, yes. And then if if you're like really into orbitofrontal, say, then what else? Huh? Field maps and phase encoding direction. So all of these fields are defined in bits, and depending on the DICOMs and the converter, they might be automatically extracted, or you might have to put them in manually. But in this case, what we are seeing here is repetition time, 1.4, and it's strictly defined that this repetition time is in seconds and has to be in seconds. And I can show you in a moment that we are actually checking this. And then here we have slice timing. This is a multi-band sequence, and therefore, time 0 happens multiple times. This is not your typical ascending, descending, because that's a little bit too imprecise. This is actually the timing of acquisition of each of the slices. So it covers multi-band sequences as well. So let me just very quickly put that where it should be and see what the validator says.
Can I say something while we're talking about?
Go for it.
So I don't know who asked about the if you have MIFIs already but you don't have the DICOMs. So the creation of that JSON file is done by DICOMs MIFI-X, and it's super useful. So you can fill it all in by hand, but it's like quite self-central.
We use a different format, and I don't even think we get the DICOMs for the Anton holes, and the functional ones come like zipped. So they come in via signature format. So it's
so if you look on the website, I'm just filling time.
Oh, it's fine. It's fine. Go for it.
If you look on its website, there's like 15 different converters, which is like really good. And so somebody at your institution, if they don't already have a converter that will work, I bet there's someone that will do it. Because as Chris said, you can get the PDF file and that you can like print out as human readable. That's fine, all the information's there, but like, what a nightmare to go and type everything in.
Oh, okay. So I have.
You're going to find task name, right?
Yes, I will. So let me I copied it instead of moving it, but this is what we have here. Let me just. Okay, cool. So we have an error. It tells us that we need to define a field called task name, which we cannot infer from the DICOMs itself because the DICOM standard doesn't know what paradigm and task was it. So let me add this. And I'm going to do, let me just do this very quickly. And then I'm going to show you some other stuff. Right. Here, what I do, basically, I can do task name, and I'm going to call it Breffold. Okay. Let me just revalidate this. Okay, great. What's the warning? All right. So you probably noticed that I don't have, this is a task, but to actually analyzing task fMRI data, there's something more than the repetition time and slice timing. I actually need to have a timing of the paradigm. I need to have a timing of the stimuli and timing of the responses depending on the paradigm. And this would be done normally in a file called events. Also a tabular file. It's a very simple structure, which is basically onsets, durations, and different categories of events. We also have ways of storing the actual stimuli. So if you're showing images or movies, there's also a place to put them. There's a lot to explore. There are a lot of different modalities, but those are the basic tools, the specification and the validator. And the tutorials out there, I recommend you to look them up. Doing this manually, I'm just going to reiterate, this is just an educational exercise. I would never do this for a real data set manually, but this is a way for me to explain what of these files mean. You're either going to automate it by writing scripts, which sometimes is necessary, especially when we just heard about like, oh, our scanners give us this weird format, they're not DICOMs, we have it zipped. Sometimes you will have to write a custom solution to do this conversion. But the standard itself is designed in a way to be rather straightforward to work with. But if your scanner produces DICOMs, you might be able to get away with a sort of a more standard automated solution called HUDICONV. And when you go to Bit Starter Kit, and one of the tutorials is how to use HUDICONV, which is a heuristic DICOM converter. So hopefully this was helpful. Tal, do we switch rooms or?
Yeah, I think so. I think you're going to move to 103.
Okay.
I'm not sure why. Probably we decided we wanted to.
It's fine. I think they're.
And Anish will be here for web development. I think Anish has like an hour and a half. You have an hour, but. This is the last thing today. You guys probably know that we have nothing scheduled in the evenings, I think, until the last night next week. So, whenever you get tired of listening to Chris and Anisha, you're welcome to wander off and figure out your dinner plans.
I've got a beer tutorial scheduled.
So what?
A beer tutorial. It's like drinking 101. All right. So basically, the next talk before I go will be about what you can do if your data is in bits, all of the different apps and all of the different services and tools you can use if your data is bits. And let me just reiterate once more, this is all a community project, so if you know people that we should reach out, please tell us. If you would like to add more modalities, more data types, please reach out. If you want to help with documentation and tutorial, please reach out. All of this is open source and all of this is by scientists for scientists. So thank you so much, and hopefully see you soon at Beer 101. Sorry, no, the other one.